So now it's time to talk about useful electrochemistry in the form of a galvanic cell which we are going to build up from scratch. And I'm going to draw this thing not by hand, but using PowerPoint. But I still think you should draw it by hand. The reason I'm using PowerPoint is so that you can download this slide later and remind yourself of how it was built up step by running it as an animated slideshow. You'll see when we're done with this section that it's a lot of information, and the first time you look at your notes after a week, it can be overload. And so it's useful to be able to quickly remind yourself of how we built up, even though eventually you just need to be able to look at one of these things and get it. So I recommend you treat this like a titration. If you're using a notebook, 2 clean sheets of paper, and use the top half of one page for just the drawing, and then all of the associated notes, which I will be writing by hand, will go everywhere else. Now, every time I animate something in, I'll make a comment, and then I'll just pause for a few seconds, which is your cue to actually press pause on the video and recreate what I've drawn. Don't kill yourself to make this look like a masterpiece, just make it look understandable. So the first thing we're going to do is just draw a couple of beakers with electrodes in them. Notice that I have left some room above and below the beakers, and that's because we have more to draw in those spaces, so make sure you leave some space as well in those areas. Next, we'll put some solution into each beaker. On the left side, to go with the zinc electrode, we have a solution of zinc 2+ ions, and we have some charge balancing sulfate ions as well. And we'll say that this is a 1 molar solution of zinc sulfate aqueous. And on the right, with the copper electrode, we have copper ion and sulfate ions. Also, let's say it's 1 molar of copper sulfate solution. Notice that these are the exact same species that we saw in our useless electrochemistry example, but already the setup looks different than what we had before. And next, we will connect those 2 electrodes with a couple of wires that we're plugging into this device here, which we'll call a voltmeter or potentiometer. We actually won't discuss what this is or what it does until later. For now, we just draw it and the connecting wires. The electrons will be able to travel through this wire, go through a device, and then reach the other side. But the question now is, which way did the electrons travel, from left to right or from right to left? To figure this out, we must discuss reduction potential. So now I'm going to write some notes. Note number 1. Electrons move toward the more positive reduction potential. Electrons move toward more positive reduction potential. And let's put reduction potential in quotes, since we haven't learned that term before. This is just the electrical potential or voltage associated with a reduction process, or reduction half reaction. So it still has the symbol E, but we're specifically talking about a reduction half reaction. And when we say it's more positive, what we mean is that it's a more favorable reduction reaction. More favorable reduction half reaction, to be more specific. Now typically, when you look up a half reaction, it's always written from the reduction point of view. So all half reactions written from reduction point of view. Red POV. And we'll see what I mean by that more clearly in a moment. But let's just tack on the line with associated E. And then we'll put this little circle or not sign up top. And this stands for standard state. And standard state means that if we have aqueous species, they are 1 molar. And if we have gas species, They are at 1 bar pressure. And so the cell that we are currently building up is at standard state because we stated that each solution is 1 molar in concentration. And so what do I mean by all of this? In our example, we have 2 reactions of interest, although I'm actually going to write out a total of 4. Starting with copper 2 plus 2 electrons is in equilibrium with copper solid. But from the forward point of view, this is a reduction half reaction, right? We're gaining electrons. And between the 2 copper species, it should be clear which one is going to gain the electrons. It doesn't make sense that copper solid gets electrons and then becomes copper 2 plus. Sometimes it's not as obvious what the reaction is going to be, but right now we're going to keep it simple. And so this reduction half reaction has a voltage associated with it. E equals 0.339 volts. At least that's the voltage associated with it when we're at standard state, which is what we're always going to find when we look these half reactions up. If we wanted to learn about voltages, if we're not at 1 molar concentration, then we need to use something called the Nernst equation, and that's just foreshadowing for the future. On the other side of the cell, the potential half reaction that can occur from the reduction point of view would be for the positive zinc 2 plus ions to gain 2 electrons and form more zinc solid. This reduction potential at standard state is equal to negative 0.762. And so clearly, one of these voltages is more positive and thus more energetically favorable than the other, and it would be our copper half reaction. So let's just note, this is more positive, and the result is electrons are going to flow towards copper. Electrons flow toward copper half cell, and we call it a half cell because it's literally half of the electrochemical cell. As for the zinc side, or the zinc half cell, well, that's where the electrons are coming from. So electrons flow towards the copper half cell from zinc half cell. In other words, zinc isn't going to be reduced, it's going to be oxidized to produce those electrons that go to copper. And so we're going to write this reaction in reverse, which will actually wind up being an oxidation reaction. So let's rewrite this as zinc solid produces zinc 2 plus and 2 electrons. And now what's its voltage when written from the reverse point of view? Well, hopefully your instincts say it's just the exact same number, but positive. And so these are in fact the 2 half reactions that are going to occur in this cell. And so to get the overall reaction of the total cell, we are going to add them together. And we get copper 2 plus zinc solid produce and eventually form an equilibrium with copper solid and zinc 2 plus. No electrons to be found because they cancel out in the math since they're on both sides of the equation. And the overall voltage or potential for this cell is equal to those 2 voltages added together. So 1.101 volts. And let's just note that I got that by taking the standard state potential of what we'll call the cathode, for reasons we'll get into momentarily, but copper is the cathode. We took that standard state voltage from the reduction point of view and then we added the standard state voltage of what we'll call the anode, i.e. zinc, but from the oxidation point of view when we flipped that sign. So this right here is just the exact same number, but the negative of the anode from the reduction point of view. Again, we will define anode and cathode momentarily. For now, I'll just say that the more positive this voltage is for the overall electrochemical cell, the more energy you can get as the cell transfers electrons from one side to the other. In other words, the more joules you can get per coulomb of charge, which is what a volt is. So back to the cell. Now we've identified which way the electrons travel throughout this cell. We learned before that the zinc will in fact be oxidized and thus produce more zinc 2 plus ions in solution. Electrons will then flow through this wire, through this device, and then out the other side, where the copper 2 plus in solution will take them and form more copper solid on top of this metal. And as the electrons are traveling through our device, they are doing some work for us. It's analogous to that water wheel. Just like the water eventually makes it all the way over here, but does some work along the way, so too do these electrons. Now let's define those cathode and anode terms I used earlier. So note 2, cathode and anode. Cathode is the electrode at which reduction occurs. Electrode at which reduction occurs. And the anode, conversely, is the same sentence, except it's at which oxidation occurs. Now I'm going to underline the words "at which" to emphasize that the cathode and anode are not necessarily reduced or oxidized themselves, they're just the electrodes at which reduction and oxidation are happening. In our example, copper solid would be considered the cathode. Copper is cathode, even though it's actually copper 2 plus that's taking the electrons and being reduced. So copper 2 plus is reduced. On the other hand, the zinc solid electrode is actually being oxidized and losing its electrons, and thus creating more zinc 2 plus ions in solution. But that's not always going to be the case, and so I think it's a common misconception. Students think cathode means that is reduced. No, that's just the electrode where the reduction is occurring. But now let's add to our visual. We will now label the zinc as the anode and copper as the cathode. Now I want to cover one more part of the cell before ending this video. But before I get to that, I want to just pose a question to you. Do you see something wrong with producing zinc 2 plus over here, or for that matter, reducing copper 2 plus over here? Pause and think. The issue is that as zinc 2 plus is formed, the overall positive charge of the left solution will increase, but not the overall negative charge, because nothing is causing the sulfates to increase with that zinc 2 plus. On the opposite side, we're losing positive charge as Cu2 plus is reduced, but we're not losing any of the negative charge. And so what's happening on both sides is a charge balance violation. And so there's only one way to stop that from happening, and it's with something called a salt bridge. Now I'll admit it's pretty crowded here. Okay, that's better. I will admit that when I first learned all of this electrochemistry, I really did not understand what a salt bridge was or its purpose. It was just this thing that was part of the cell. So I want to try to demystify it for everyone. We'll make some notes about it momentarily, but first I'm just going to describe it using this visual. Here we have a salt bridge full of a KCl electrolyte solution, and its purpose is to maintain charge balance or electroneutrality in both half cells. So on the left side, the issue is that we are accumulating too much positive charge. Well, the salt bridge will just move chloride ions into this solution to balance that positive charge. If a zinc 2+ is created, 2 Cl- ions go into solution. The idea is these chlorides are unreactive. They're just going to be spectator ions. All they do is balance the charge. Conversely, as this side loses positive copper ions, 2 K+ ions will go in to take each copper ion's place. Once again, these are non-reactive in principle. They are just helping to charge balance these excess sulfate ions that aren't going anywhere. So let's quickly write some notes about the salt bridge. 3. Salt bridge. This is for conducting ions in and out of cells to maintain electroneutrality. For conducting ions. For conducting ions in/out of half cells to maintain electroneutrality. Maintain electroneutrality, i.e. charge balance. These typically contain some type of a salt solution, hence the name. Typically contains a salt solution. For example, KCl would be the most common that we'll see. Next, let's just add a couple of notes to the visual and call it a day. On the visual, let's just draw some arrows to show how the ions can flow in and out of that salt bridge. There are the two ideas that I've already covered, that the chloride could enter the solution on the left side and thus increase the negative charge to compensate for that excess positive charge. Or another option, not as common to consider in this class, is maybe that salt bridge could take some of those positive ions out of the solution. So zinc 2+ could leave the solution and decrease that excess positive charge. On the right side, we have a similar situation. K+ will enter the solution, which is what I already described, to compensate for the loss of positive charge. Or maybe the salt bridge could take negative sulfate out of the solution. So that's a fair amount of information about this cell. We definitely have more notes to write, but that's enough for today.